this video, we're going to look at another induction example. We're going to look at a proof by induction that deals with divisibility. So first, let's introduce a new symbol. A, and then this vertical line, B, means that A divides B. That's how we would say that. A divides B. What that means is that there's some number that I can multiply by A, some integer, to get B. So if I try to do B divided by A, that means I'm going to get some integer m. Where m is an integer. Let's look at a real number example here. I know that, let's see, 4 divides 20 because 20 divided by 4 is equal to 5. And 5, of course, is in the set of integers. So all that's saying, A divides B, means that B is some multiple of A, just like 20 is some multiple of 4. But it's just another way of saying that. Another way of writing this sentence right here that I have in yellow, if I just multiply both sides by A, I can say that B is equal to A times m. But again, it's very important to note that m has to be an integer, otherwise it doesn't fit our definition. To practice this idea of divisibility, let's just look at a couple more quick examples. 3 divides 12. Is this a true statement or a false statement? Well, I have to see if there's an integer that I can multiply by 3 that will give me 12. One way of finding that is investigating 12 divided by 3. I know 12 divided by 3 is equal to 4. Is 4 an integer? Yeah, 4 is an integer. I have to make sure that I get an integer out. Now I know that 3 does divide 12. That is a true statement. I can also think of this as rewriting the number 12 as 3 times some integer m, and in this case that integer is 4. That's why 3 divides 12. So now you're hopefully realizing 3 divides 13, true or false? This is definitely going to be false. I can't find an integer, so there is no integer m such that 13 is equal to 3 times m. You could check that by doing 13 divided by 3. And you're going to get 4.33333, which is not an integer. 4.3 repeating is not an integer. So that's just some quick examples of what this symbol means. Let's see how we could apply that to a proof. Use math induction to prove that 5 divides 6 to the power of n minus 1 for all integers n. We're going to use math induction here because we're trying to prove something about all natural numbers. So of course the first thing we need is our base or lowest case. In this case, n is going to be equal to 1. So let's show that this is true for n equals 1. 6 to the 1 minus 1 is equal to 6 minus 1, which is 5. Does 5 divide 5? Yes, because I can rewrite 5 as 5 times 1, and 1 is an integer. I can check 5 divided by 5 equals 1, and 1 is an integer, or I can rewrite 5 as 5 times 1. So what we've shown is that our base case does hold true. Now for our induction assumption. Assume for some natural number k, and then we also have to say that k is not the lowest case here, because we already proved it for that. So for some k bigger than 1, we're going to assume that it's true. 5 divides 6 to the k minus 1. Then, using how I rewrote our statements, I can say that 6 to the k minus 1 is equal to 5 times some integer m. That's just the definition of divisibility. I can test this by saying 6 to the k minus 1 divided by 5 equals an integer, and then I just multiplied each side by 5. So that's our induction assumption. We are assuming this to be true. Our next job is to show that this is true for k plus 1. Show that 6 to the k plus 1 is also divisible by 5. So let's investigate 6 to the k plus 1 minus 1. I have to show that our statement is true for k plus 1, using what I've underlined in red. Well, by our exponent rules, I know that 6 to the k plus 1 can be rewritten as 6 to the k times 6 to the 1, and then I still have that minus 1. So notice I'm using exponent properties here. I have two numbers with the same base. I can add their exponents. K plus 1 is their exponent on 6. I just kind of use that property in reverse. 6 to the k plus 1 equals 6 to the k times 6 to the first. And then that minus 1 is still there. Now it's time to use our induction assumption, what I've underlined in red. But I don't see a 6 to the k minus 1. I see a 6 to the k times 6 minus 1. Well, let's solve for 6 to the k in our induction assumption. I can say that 6 to the k is equal to 5m plus 1. All I did was add 1 to both sides. Now it's in a more usable form because I can take that 6 to the k and substitute it in for this 6 to the k because I can use my induction assumption as truth. Well, 6 to the k is 5m plus 1, so I'm just going to rewrite this as 5m plus 1. Remember, m was an integer, times 6 minus 1. Remember our goal. We're trying to show that 6 to the k plus 1 minus 1 is equal to 5 times some integer. That's what I'd like. Let's keep going with what we have. I'm going to take this and distribute our 6, and we get 30m plus 6 minus 1, which is 30m plus 5. Now I'm going to move on to the next slide so I have more room. Just to recap, we were starting with this, and we've shown that is equal to 30m plus 5 from my work on the previous slide. I'd like to know or see if this is equal to 5 times some integer. Well, turns out we can factor out a 5 from this expression, and we're left with 6m plus 1. So what this says is that 6 to the k plus 1 minus 1 is equal to 5 times something. Now, it just remains to show that 6m plus 1 is an integer. Because remember from our example, 3 didn't divide 13 because 4 1/3 wasn't an integer. So I can't say that 5 divides 6 to the k plus 1 minus 1 unless I explicitly say that this is an integer. Do I know that it's an integer? Yes. Here's why. 6m plus 1 is an element of integers because all three values you see in here, 1, 6, and m, are all integers. 1 is very clearly an integer, the number 1. 6 is very clearly an integer. And m is definitely an integer because I defined it that way in my induction assumption. Now, is it true that every time you multiply two integers, you get an integer? Yes. And that word that we would use is closure. Integers are closed under multiplication. So 6m is also an integer. Is it true that if we add two integers, we get an integer? Yes, because integers are also closed under addition. So I have to say that last piece. 6m plus 1 is an element of the integers because 1, 6, and m are elements of integers, and integers, or the set z, is closed under multiplication and addition. Without saying that last part, I'm not convinced that 6m plus 1 is an integer. And without knowing that 6m plus 1 is an integer, I'm not sure that 5 divides 6 to the k plus 1. But now that we've said that, because we've talked about closure, I do know that that's true. Therefore, our statement was true for k plus 1. That's what we just showed. So, we assumed it to be true for n equals k. We showed it to be true for n equals k plus 1. Therefore, we've kind of knocked down all the dominoes. Therefore, 5 divides 6 to the n minus 1 for all natural numbers n. And I think we finished up our proof. We showed our base case. We showed that we assumed that 5 divides 6 to the k minus 1, and we showed that 5 divides 6 to the k plus 1 minus 1. It just took a little bit of finesse and some maybe new vocabulary here that we used, but it's all very important. Good luck!